Right now, as you sit still, tiny particles are passing through you. Through your hand, your chest, the top of your skull. About one of them crosses every thumbnail-sized patch of you each minute. They are called muons, and they were born 7 miles up, where cosmic rays from dying stars slam into the thin upper air. Here is the strange part. A muon lives for barely 2 millionths of a second, far too short a life to ever reach the ground, and yet it arrives anyway, in its countless billions. And the tiny magnet that each one carries has, for years, seemed to disagree with our finest theory of reality by an amount no one could explain. That number is called G-2. If slow, careful walks through real physics are your kind of thing, consider subscribing. We will build the whole idea up one step at a time, starting with the muon raining down through you right now. Sit still for a moment and notice how solid the world feels. The chair holds you, the floor holds the chair. Nothing seems to be moving through you, and yet, in the time it takes to read this sentence, dozens of particles have passed clean through your body without touching a thing. They came down from the sky. Most of them are muons, and they are arriving constantly, day and night, indoors and out, through your roof and your skin and your bones, at a rate of roughly 1 through every fingernail-sized patch of you each minute. You have never felt a single one. They begin far above your head. A cosmic ray, usually a single proton flung out of some violent place in the galaxy, comes screaming into the top of the atmosphere at nearly the speed of light. About 10 or 15 miles up, it slams into the nucleus of an atom in the air. That collision is so hard that it shatters into a spray of new particles, the way a struck rack of pool balls scatters, except that here the energy is high enough to make matter from motion. Among the debris are short-lived particles called pions, and when those pions break down, muons are what come pouring out, racing downward in a soft, invisible rain. So a muon is a piece of the sky reaching the ground. That alone is worth sitting with. The light from those distant cosmic events never reaches you, but a physical fragment of the event, made fresh in our own air, passes through your hand while you sit reading. It is one of the few ways the violent universe touches you directly and gently at the same time. For now, hold a simple picture of what a muon is. Think of it as a heavier, short-lived twin of the electron, the same particle that flows through every wire in your home. It carries the same amount of electric charge. It spins in the same way. It is, by every test we can run, a point with no size at all. The only real difference is that it is heavier, and because it is heavier, it does not last. Within a couple of millionths of a second it falls apart into lighter particles and is gone. That short life is the first puzzle, and we will come back to it, because by every simple estimate a muon should die long before it ever reaches the ground. It does not. It arrives in its billions. The reason it survives the trip is one of the most direct proofs we have that time itself bends with motion, and that single fact turns the muon from a curiosity into a kind of messenger. But the deepest puzzle is not the journey. It is the tiny magnet the muon carries. Because it is a spinning electric charge, every muon behaves like an unimaginably small bar magnet, and the exact strength of that magnet is a number we can both measure in a laboratory and calculate from theory. For decades, those two numbers, the measured one and the calculated one, refused to match. The gap was absurdly small, buried in the 11th digit, far too fine for any ordinary instrument. And yet a careful enough experiment could see it, and theory could predict it, and they disagreed. That disagreement is what sent a quiet unease through physics. This whole story is the story of that one number. We are going to build it slowly, starting from nothing. We will meet the people who found the muon by accident, the equation that said its magnet should be a clean, round value, and the discovery that the clean value was wrong in a way that opened a door. The muon is still passing through you as you read. By the end, you will understand why a single digit deep inside it has kept careful, sober people awake at night. The muon was not predicted. Nobody went looking for it. It walked into physics uninvited, on a photographic plate, in 1936, and at first almost nobody knew what they were looking at. The place was the California Institute of Technology, and the people were Carl Anderson and his student Seth Neddermeyer. Anderson was young, barely 30, and already had a habit of finding things that should not have been there. A few years earlier, in 1932, he had spotted the positron, the antimatter twin of the electron, a particle whose existence had been predicted on paper but never seen. He had found it using a device called a cloud chamber, and now he was using the same kind of device to study cosmic rays. A cloud chamber is a beautifully simple thing. It is a sealed box filled with vapour that is right on the edge of forming droplets, like air just before a fog. When a charged particle shoots through, it knocks electrons off the atoms along its path, and droplets condense on that disturbed trail. The result is a thin white streak hanging in the air, a vapour contrail in miniature, marking exactly where the particle went. If you put the chamber inside a magnet, the particle's path curves, and the way it curves tells you its charge and gives you a handle on its mass. A heavy particle barely bends, a light one curves hard. Anderson and Neddermeyer kept seeing tracks that bent the wrong amount. The particles were clearly charged because they curved, but they curved too gently to be electrons, which are feather-light and swerve sharply, and too sharply to be protons, which are heavy and plough almost straight ahead. Whatever was making these tracks sat in between, in a no-man's land of mass where nothing was supposed to live. It was something like 200 times heavier than an electron, yet far lighter than a proton. This was unsettling, because in 1936 the list of known particles was very short. There was the electron, the proton, the photon of light, and the recently found neutron and positron. That was nearly the whole cast. Physics felt for a brief moment almost finished. To find a brand new particle with a mass that fit nothing was like cataloguing every animal in a forest, declaring the work done, and then watching an unfamiliar creature stroll out of the trees. Anderson was cautious. Extraordinary tracks could come from ordinary mistakes, from a fast particle that looked slow, or a chamber that was misbehaving. So he and Neddermeyer gathered more images and stacked thin plates of metal inside the chamber to slow the particles and measure how they lost energy. The new particle kept showing the same in-between behaviour again and again, until the conclusion could no longer be avoided. There was a middleweight particle raining down from the sky, and it was real. Notice what they had actually caught. These were the same muons we have been talking about, the ones passing through you now, captured at the moment they revealed themselves. The cosmic rain that feels so abstract first became visible as a set of faint curved lines on photographs from a hilltop in California. The discovery answered one question and opened a harder one. They knew the particle existed and roughly what it weighed. They had no idea what it was for. In the tidy physics of the day, every particle seemed to have a job. The electron carried current. The proton built the nucleus. This new middleweight thing did nothing anyone could name. It simply appeared, lived briefly, and died, and that uselessness would become one of the most famous complaints in the history of science. To understand why, we have to back up 1 year to a prediction made in Japan. A year before the Muon turned up in Anderson's cloud chamber, a young Japanese physicist named Hideki Yukawa had predicted a new particle of almost exactly the right weight, for completely the wrong reason. The coincidence would tangle up physics for a decade. Yukawa was trying to solve a problem about the nucleus. Inside every atomic nucleus, protons are packed together tightly, and protons all carry positive charge, so they should furiously repel one another and fly apart. Something stronger than that repulsion has to hold them. Yukawa proposed that the protons and neutrons were tossing a particle back and forth between them, and that this constant exchange acted like a glue. From the known size of the nucleus, he could estimate the weight of the glue particle, and he found it should be a couple of 100 times heavier than the electron. He called it a mesotron, a middleweight, from the Greek word for middle. Then, 1 year later, Anderson and Neddermeyer found a middleweight particle falling out of the sky. The mass was close. The The fit looked too good to be a coincidence. For years, most physicists simply assumed the cosmic ray particle was Yukawa's nuclear glue, arriving at the ground after being knocked loose high in the atmosphere. The new particle had been handed a job, and the job was one of the most important in nature. There was only one problem, and it took a clever wartime experiment to expose it. If this particle really was the glue of the nucleus, it should feel the strong nuclear force powerfully. Fire it into a block of matter, and it should be grabbed almost instantly by the first nucleus it passed, sucked in and consumed. In 1947, 3 Italian physicists, Marcello Conversi, Ettore Pancini, and Oreste Piccioni, working through the dangers of war-torn Rome, measured what actually happened when these particles stopped inside materials. The negative ones, slowing to a halt near a nucleus, should have been devoured at once. They were not. The particles lingered, ignoring the nucleus right beside them, behaving as if the strong force barely noticed them at all. Whatever was raining from the sky felt the nuclear glue force about 1 trillion times too weakly to be the glue itself. The beautiful match between Yukawa's prediction and Anderson's discovery had been an accident of weight and nothing more. 2 different particles of similar mass had been mistaken for one. The knot came untied that same year. In England, Cecil Powell and his group, studying cosmic rays with sensitive photographic emulsions carried up mountains, found the real Yukawa particle at last. They saw a heavier particle arrive, stop, and promptly decay into the lighter one that Anderson had been watching all along. The heavier one was the true nuclear glue, and we call it the pion. The lighter one, the decay product, was the imposter, and we call it the muon. The pion was born high in the air, lived for a flicker, and broke down into muons. Anderson had been seeing the children, not the parent. So the muon was demoted from nuclear hero to apparent freeloader. It did not build the nucleus. It did not glue anything. It was simply a heavier copy of the electron that nobody had asked for and nobody could explain. The famous reaction came from the physicist Isidore Rabi, who, on hearing that this useless extra particle was confirmed, is supposed to have asked, with a mix of irritation and wonder, who ordered that. The line stuck because it captured exactly how the muon felt to everyone. It was an extra dish nobody had requested sitting on the table, and the kitchen could not say why. To make sense of it, we first have to say clearly what kind of thing it actually is. To say what the muon is, it helps to sort the particles of nature into a couple of families, because the muon belongs to one of them very cleanly, and its family tells you most of what you need to know. Some particles feel the strong nuclear force, the powerful glue we met in the last chapter. Protons and neutrons do. The pion does. These are the heavy, sociable particles that crowd into nuclei and stick. But there is a second family that ignores the strong force entirely, and the founding member of that family is the electron. These standoffish particles are called leptons, from a Greek word meaning light or slight, and the muon turned out to be a lepton through and through. That single fact explained the Italian experiment in one stroke. The muon refused to be eaten by the nucleus because, like the electron, it simply does not answer when the strong force calls. So picture the electron, the familiar particle that fills the outer parts of every atom and flows as electric current. Now imagine an exact copy of it. Same negative charge, to the last decimal, same spin, the same complete lack of any measurable size, behaving in every experiment as a true point. The copy is identical in every way but one. It is heavier, about 207 times heavier to be precise, which means a single muon weighs as much as 207 electrons stacked together, while still being a sizeless point. That extra heft is the muon's only real distinction, and from it everything else follows. Here is the everyday way to feel the difference. Imagine 2 balls thrown at the same speed, a ping-pong ball and a billiard ball. They are the same shape and move alike, but the heavy one carries far more punch and is far harder to stop or turn. The muon is the billiard ball to the electron's ping-pong ball. Same rules, more mass. The comparison is rough though, and it breaks in a way that matters. Real balls are made of smaller parts and have a size you can measure. The muon does not. As far as we can tell, it has no parts and no width at all. It is pure point-like charge that simply happens to weigh more, and physics has no agreed reason why such a thing should exist. That is the heart of Rabi's complaint. Nature did not need a second, heavier electron. The first one was doing fine. And yet there it is, and stranger still, it is not even the last copy. Decades later, physicists found a third version, heavier again, called the tau, weighing in at about 17 times the muon. So we have three near-identical leptons of rising weight: the electron, the muon, and the tau, three rungs of the same ladder, differing only in mass, and to this day no one can say why there are three rather than 1 or 7. These three form what physicists call the three generations of charged leptons, and the pattern echoes elsewhere among the particles, as if nature wrote out its alphabet 3 times in heavier and heavier ink. The muon sits squarely in the middle generation. Heavy enough to be unusual, light enough to make in great numbers, it became the perfect particle to study closely. The electron is so light and stable that it gives away few secrets. The tau is so heavy that it dies almost the instant it is born, before you can do much with it. The muon falls right in the useful middle, but that middle position comes with a price, and the price is time. Being heavier than the electron, the muon is not content to simply exist. It is unstable, primed to fall apart into lighter pieces at the first opportunity. And it takes that opportunity astonishingly fast. Which brings us to the strange matter of how a particle that barely lives long enough to be born ever survives the long fall to the ground. A muon, left to itself, lasts about 2/millionths of a second. Written out as a fraction, that is roughly 2/1,000,000 of a second, an interval so short that, in human terms, it is no time at all. In that flicker, the muon breaks apart. It turns into an electron and 2 of the ghostly, nearly weightless particles called neutrinos, and then the muon is simply gone, its identity spent. That lifetime is not a guess. You can make muons in a laboratory, hold them, and watch them vanish, and they always fade at the same average pace, like a vast crowd of identical hourglasses all started at once. Half are gone after one interval, half of those after the next in the steady thinning that physicists call decay. The muon is, in this sense, one of nature's most reliable clocks. It does not care what made it or where it is, it simply counts down. Now bring back the muons raining through you, and a real problem appears. They are born about 10 miles up, even racing downward at nearly the speed of light, the fastest speed anything can go. A muon covers only about 1/3 of a mile in 2/millionths of a second. By that arithmetic, the overwhelming majority should die in the upper air, far above the tallest mountain, and almost none should reach the ground. We should be standing at the bottom of a sky that swallows them whole. Instead, they pour down in such numbers that one crosses your fingernail every minute. The simple sum is off, not by a little, but by an enormous factor. Something is wrong with the bookkeeping. The resolution is one of the strangest true things in physics, and it was confirmed with muons themselves. In 1941, 2 physicists, Bruno Rossi and David Hall, carried muon detectors to the top of a mountain in Colorado and then down to a lower altitude, and they counted how many muons survived the descent. Far more arrived than should have. The muons were living longer than their own internal clock allowed, and the faster they moved, the longer they lasted. The reason is that time does not run at a fixed pace for everything. According to Albert Einstein's theory of special relativity, a clock that moves very fast as measured by someone standing still ticks more slowly. This is not an illusion or a trick of measurement. It is how time actually behaves. For something moving at nearly light speed, the slowing is dramatic. From the muon's own point of view, its life is still the usual brief 2/millionths of a second, and it does not travel far at all. But from our point of view on the ground, the muon's internal clock is crawling, so its short life is stretched out long enough to carry it all the way down through the atmosphere. You can flip the picture to the muon's side and it still works. To the Muon, time is normal, but the distance to the ground is shrunk. The 10 miles of air it must cross is squeezed by its tremendous speed into a short hop it can easily make before dying. Each viewpoint tells a different story, one of stretched time and one of shortened space, and remarkably both give the same answer. The Muon reaches the ground. This is why the Muon is more than a curiosity. Every Muon that lands on your skin is a tiny demonstration that time bends with motion, an experiment nature runs over your head every second of every day. The particle that nobody ordered turned out to be a free, endless proof of relativity. We have its weight, its family, and its strange stretched life. Now we come to the property that this whole story turns on. The Muon spins, and because it spins and carries charge, it is a magnet. The exact strength of that magnet is the number that has kept physicists awake. Every Muon spins, and to understand the rest of this story you have to take that spin seriously, while also being careful not to picture it too literally. When we say a Muon has spin, we do not mean it is a little ball turning on an axis the way the Earth does. It is a sizeless point, so there is no surface to rotate. Spin is a built-in property, as fundamental as charge, a fixed amount of angular motion that the particle simply has and can never gain or lose. The electron has it. The Muon has it. It comes in a set, unchangeable quantity. The honest thing to say is that spin is real and measurable, even though our mental image of a spinning top only half fits. We keep the word because the particle behaves, in many ways, as if it were genuinely turning. And here is why that matters. A Muon carries electric charge, and a moving electric charge makes a magnetic field. This is not exotic. It is the principle behind every electromagnet and every electric motor. Send current around a loop of wire, and you create a magnet with a north and a south, a coil that can pick up nails. Now take a single charged particle and let it spin, and you have in effect the tiniest possible loop of current. So a spinning charged particle is a minuscule magnet, complete with its own north and south poles. The Muon is one of the smallest bar magnets that can exist. The strength of that little magnet is what we want to pin down. Physicists capture it in a single number, and that number has a name. It is called the G factor. You can think of the G factor as a dial that sets how strong the Muon's magnetism is for a given amount of spin. Turn the dial up and the magnet is stronger, turn it down and it is weaker. Every property of the Muon's magnetism, everything we can measure about it, is folded into this one value of G. Hold a concrete picture for what this magnet does. Place the Muon in a magnetic field, in the pull of a larger magnet, and it does not simply snap into line. Instead, it wobbles. Like a spinning top that has been tipped, with the Earth's gravity tugging at it, the Muon's spin axis swings slowly around in a steady cone. A tilted top traces a circle with its handle while it spins. The Muon's spin traces a similar circle as the magnetic field tugs on it. This stately wheeling is called precession, and the speed of that precession depends directly on the G factor. A stronger little magnet wheels around faster in the same field. That link is the key that unlocks everything later. Because the precession speed depends on G, you can measure G without ever touching the Muon. You put Muons in a known magnetic field, you watch how fast their spins wheel around, and from that rate you read off the strength of their magnetism to extraordinary precision. The wobble is the Muon telling you, out loud, exactly what kind of magnet it is. Much later in this story, a giant ring full of circling Muons will do precisely that, and the number it whispers back will be the heart of the mystery. The comparison to a spinning top is useful, but remember where it stops. A real top slows down, tips over and falls, because friction and air drain its motion away. The Muon's spin never slows and never falls. Its precession is pure and frictionless, set only by the field and by G, until the Muon decays and the show simply ends. So the whole drama narrows to a single question. What is the value of G for the Muon? At first glance you might expect some messy, arbitrary number. Instead, the first real answer, handed down by one of the most beautiful equations in physics, was startlingly clean. It was simply 2. In 1928, a quiet, intensely private English physicist named Paul Dirac was trying to fix a mismatch between 2 great theories, and in solving it, he accidentally predicted the Muon's magnet, antimatter, and a good deal of the modern world, all from a single line of mathematics. The mismatch was this: quantum mechanics, the new physics of the very small, described the electron beautifully but ignored Einstein's relativity, the physics of the very fast. Relativity described fast motion beautifully but ignored the quantum world. The electron is both small and fast, so it needed an equation that honoured both at once, and no one had written one. Dirac set out to find it, working in the abstract, demanding that his equation be consistent with relativity and with the quantum rules at the same time. The equation he found is now simply called the Dirac equation, and it is carved on a memorial to him in Westminster Abbey. It worked, and it did something no one asked it to do. Tucked inside the mathematics with no extra assumptions was spin. Dirac had not put spin in by hand. It fell out on its own, as a necessary feature of any electron that obeys both relativity and quantum mechanics. The property we struggled to picture in the last chapter turned out to be built into the deep structure of the particle, demanded by the universe's own rules, and the equation said more. It predicted the exact strength of the electron's little magnet. It set the G-factor, the dial we just met, to a clean and specific value, not some ragged decimal, but exactly 2. For a simple point-like particle of charge and spin, Dirac's mathematics insisted the magnetism had to be precisely twice what an old classical guess would have given. The number 2 was not measured first and explained later. It was predicted, cold, from pure theory, and then experiments on the electron confirmed it. The G-factor really was, to the accuracy of the day, exactly 2. This was a triumph of a rare and pure kind. A man working with paper and consistency alone had told nature what one of its numbers must be, and nature obeyed. The same equation applies to the muon, since the muon is the electron's heavier twin and follows the identical rules. So the muon's G-factor too should be exactly 2. That clean 2 is the bedrock of our whole story. It is the value everything will be measured against. The equation had one more surprise, and it was the strangest of all. To work properly, it required twice as many solutions as expected. Half described the ordinary electron, the other half described something with the same mass but the opposite charge, a mirror image particle that should not exist in a world made only of ordinary matter. Dirac, uneasy, eventually accepted what the mathematics was telling him. There must be an antimatter twin of the electron, identical in every way but with positive charge instead of negative. You have already met the proof. The positron that Carl Anderson spotted in his cloud chamber in 1932, 4 years before he stumbled onto the muon, was exactly Dirac's predicted antimatter electron caught in the act. The same cosmic rain, studied by the same careful man, first confirmed antimatter and then delivered the muon. Dirac's single equation had reached out and predicted a whole hidden half of nature. So by the late 1920s, the picture looked complete and gorgeous. A point particle with charge and spin had a G-factor of exactly 2, full stop, proven by theory and backed by experiment. There was nothing more to measure. The dial sat at a perfect round value, and the matter seemed closed, but it was not closed. 20 years later, a sharper measurement and a sharper mind would show that G is not exactly 2 after all. It is a tiny, fateful sliver more. For about 20 years, the G-factor of exactly 2 stood as settled fact. Then, after the Second World War, experiments grew sharper, and a small discrepancy crept into view. The electron's magnet was not quite at the clean value Dirac had predicted. It was a hair too strong by about 1 part in 1,000. The dial did not read 2. It read something like 2.002, with the interesting story living entirely in those trailing digits. A part in 1,000 is a tiny excess, but it was real, and it demanded an explanation. The man who found it, in 1948, was the American physicist Julian Schwinger, a prodigy who had been doing serious physics since his teens and who worked with a formal, almost musical precision. He took the new tools of quantum field theory, the deeper successor to Dirac's equation, and asked what they predicted for the strength of the electron's magnet when calculated more carefully than Dirac had been able to. The answer revealed something profound about empty space, and to feel it, you have to let go of the idea that the muon, or the electron, is ever truly alone. In Dirac's clean picture, the particle sits by itself and has its magnet, and that is that. In the truer picture, no particle is ever isolated. It is constantly interacting with the space around it, and that space is not empty. It seethes. The particle is forever sending out and reabsorbing fleeting flickers of energy, brief disturbances that pop into being and vanish again, and each of these flickers nudges the particle's magnetism a little. Schwinger calculated the simplest and largest of those nudges. He found that the electron's G-factor should exceed 2 by a specific calculable amount, and the size of that excess was set by one of nature's most famous numbers, the fine structure constant, written as the Greek letter alpha. This constant, roughly 1/137, measures how strongly charged particles interact with light and with electric fields. Schwinger's correction to the magnet was alpha, divided by 2 times pi, which works out to about 1 part in 800 or 0.00116. Add that to Dirac's 2, and you get a G-factor a sliver above 2, exactly matching the new experiments. This result was so important and so beautiful in its compactness that the equation for it, alpha over 2 pi, is carved on Schwinger's gravestone. It deserves the honour. In one short expression, it announced that the round number 2 was only the beginning, the value a particle would have if space around it were truly empty and quiet. The real value is slightly larger, and the difference comes from the restlessness of the vacuum itself. Physicists gave the excess a name. They defined the anomaly as the amount by which G rises above 2 divided by 2, and they wrote it with a small letter a. So the muon's anomaly, written a mu, is just this measure of how far its magnet strays from Dirac's clean prediction. For the muon, as for the electron, that anomaly is about 1 part in 800 at the simplest level, dominated by Schwinger's alpha over 2 pi. From now on, the whole story lives inside that small number a. The clean 2 is the floor. The anomaly is the message written just above it. And the message is rich, because Schwinger's term is only the first and biggest of an endless series of nudges. The vacuum's flickers come in many forms, simple and complicated, and each contributes its own tiny correction to the magnet, smaller and smaller, layer upon layer. To measure the anomaly precisely is to read off the combined whisper of all of them at once. So before we can understand why the muon's whisper seemed wrong, we have to look closely at the thing doing the whispering. We have to look at what the empty vacuum is actually full of. The vacuum is the emptiest thing we can imagine, and according to our best physics, it is not empty at all. Understanding why is the key to the whole muon mystery, because the muon's magnet is set in part by whatever is hiding in the supposedly empty space wrapped around it. Start with the everyday picture and honour it. When you pump all the air out of a jar, you cool what remains a vacuum, and you think of it as nothing, a perfect void where truly nothing is happening. For ordinary purposes, that picture is fine, but push down to the smallest scales and shortest times, and quantum physics tells you the void is restless. Empty space is filled with a faint, ceaseless fizz of activity, particles flickering into being and vanishing again before they can be caught. They are called virtual particles, and they are borrowed, briefly, from the energy of the vacuum itself. The rule that allows this is one of the strangest in quantum mechanics. Nature permits energy to be borrowed, as long as it is paid back fast enough. A larger loan must be repaid sooner. So the vacuum is always taking out tiny fleeting loans, conjuring a particle and its antimatter twin out of nothing, letting them exist for the briefest instant, and then erasing them as the debt comes due. This happens everywhere, all the time, in every cubic inch of seemingly empty space. including the space inside you. The void is not still. It is a quiet, constant boil. Now place a muon in that boiling vacuum. The muon is not a bare point sitting in nothing. It is surrounded by a shimmer of these flickering virtual particles, popping up around it and falling back, and the muon is constantly interacting with them. It emits a flicker of light and reabsorbs it. It is briefly accompanied by a virtual pair that springs up nearby and then annihilates. Each of these brief encounters tugs, ever so slightly, on the muon's magnetism. The muon you measure is therefore never the lonely particle of Dirac's clean equation. It is a muon wearing a fluctuating cloak of borrowed activity, and that cloak shifts its magnet away from the simple value of 2. This is exactly what Schwinger calculated. His alpha over 2 pi was the contribution of the simplest possible flicker, the muon briefly emitting and reabsorbing a single particle of light. To picture and track all the more complicated flickers, the physicist Richard Feynman invented a way of drawing them, simple line sketches now called Feynman diagrams. Each diagram is a little story of what the muon might do, which virtual particles it might conjure and reabsorb, and each one corresponds to a precise piece of arithmetic. Add up the diagrams and you get the prediction for the magnet. The theory that governs all of this, the interplay of charged particles and light, is called quantum electrodynamics, or QED. It was built into its mature form in the late 1940s by Feynman, by Schwinger, and independently by the Japanese physicist Shinichiro Tomonaga, with the young Freeman Dyson showing that their different-looking methods were secretly the same. QED is the most precisely tested theory in all of science. Its predictions for the electron's magnet match experiment to more than 10 decimal places, an agreement so fine it is like measuring the distance across a continent and being off by less than the width of a hair. Here is the part that turns the magnet into a mystery, and it is worth saying plainly. The virtual particles in the muon's cloak are not only particles of light. They can be any particle that exists, including heavy ones, including, in principle, particles we have not yet discovered. Every type of particle in nature gets a chance to flicker briefly around the muon and leave its fingerprint on the magnet. So the anomaly is not just a test of light and electrons, it is a census of everything that can possibly exist. And that is precisely why the muon, rather than its lighter twin, became the particle to watch. If the electron and the muon are near identical twins, you might fairly ask why physicists chase the muon's magnet so hard, when the electron's is far easier to measure and far better understood. The answer is that the muon, because it is heavy, is a better listener. It hears particles the electron cannot. Recall that the magnet of either particle is shifted by the cloak of virtual particles flickering around it, and that the cloak can contain any kind of particle at all, including heavy ones we may not have discovered. The crucial fact is that heavy virtual particles do not affect every lepton equally. A heavy flicker tugs much harder on a heavy particle than on a light one. More precisely, the sensitivity grows with the square of the lepton's mass. Because the muon is about 207 times heavier than the electron, and 207 squared is roughly 40,000, the muon is some 40,000 times more sensitive to heavy unknown particles than the electron is. Let that sink in, because it is the reason for everything that follows. The electron's magnet, measured so exquisitely, is almost entirely set by the light. Familiar contents of the vacuum, the flickers of light and the lightest particles. Heavy newcomers barely register. The electron is a wonderful test of QED, but a poor detector for the unknown. The muon is the opposite. Its greater weight makes it lean in toward the heavy, rare and hidden, so that any massive new particle lurking in nature would leave a far bigger thumbprint on the muon's magnet than on the electron's. Think of it as a question of ears tuned to different sounds. The electron hears only the loud, nearby everyday voices in the vacuum and reports them with breathtaking accuracy. The muon, heavier, can also catch the faint, deep voices coming from far away, from massive particles that flicker only rarely and briefly. If something new and heavy exists, the electron will likely miss it entirely, while the muon may just catch its whisper. The comparison is not perfect, since both particles obey the same physics and there is no real sound involved, but it captures the truth that mass buys reach. This is why the muon's anomaly is such a prized number. It is one of the few quantities in physics that we can both measure with extreme care and calculate with extreme care, and that is at the same time sensitive to particles we have never seen. Most experiments that hunt for new heavy particles do so by smashing things together at enormous energy, trying to make those particles directly, which requires gigantic machines. The muon's magnet offers a different and quieter path. You do not have to create the new particle outright. You only have to detect the faint shift it leaves behind as it flickers, for an instant, in the cloak around a muon. There is a sharpening of this idea that most retellings skip. The tau, the third and heaviest lepton, would be even more sensitive, since it is heavier still. By the mass squared rule, it would be a far better antenna than the muon. But the tau is hopeless to use because it lives only a tiny fraction of even the muon's brief life, dying almost the instant it forms. There is no way to gather a beam of taus and watch their magnets wheel around. So the muon sits at a sweet spot, heavy enough to listen deep, yet long-lived enough to be marshalled into a working experiment. It is the most sensitive lepton we can actually use. So the strategy comes into focus. Measure the muon's anomaly as precisely as humanly possible. Calculate from the known particles of nature exactly what that anomaly should be. Then compare. If the two agree, the known particles are the whole story. If they disagree, something is missing from our list. Some particle or force flickering in the cloak that we have not yet named. The size of the gap is the size of the mystery. That gap is the number we turn to next. We can now state the central idea of this whole story in plain terms. There are two numbers. One is what we measure for the muon's magnet, in a laboratory, by watching real muons. The other is what we calculate the magnet should be, by adding up the contributions of every known particle flickering in the vacuum. The entire drama lives in whether those two numbers match. Both numbers are versions of the anomaly, the tiny excess of the g-factor above 2 that we have been building toward. On the measurement side, you take muons, put them in a magnetic field, and watch how fast their spins wheel around, reading off the strength of their magnet from that precession. On the theory side, you sit down with the known laws and the known particles and you compute, diagram by diagram, flicker by flicker, what that same magnet ought to be. The hope and the fear is in the comparison. If the measured anomaly and the calculated anomaly agree perfectly, that is a stunning confirmation that our list of nature's particles is complete, at least for anything heavy enough and common enough to matter. It would mean the cloak around the muon contains only the particles we already know, with nothing hidden. That is a triumph, though a quiet one, the kind that closes a question rather than opening a door. But if the two numbers disagree, if the muon's measured magnet is even slightly stronger or weaker than all the known particles can account for, then something is flickering in that cloak that we have not yet put on our list. Some particle, some force, some piece of nature we have never directly seen would be making its presence felt through the tiny tug it leaves on the muon's magnet. The gap between measurement and theory would be a number with a message, and the message would be that physics is not finished. There is more out there, and the muon has just felt it pass. This is what makes the muon's anomaly one of the most important single numbers in physics. It is a sealed letter from the unknown. We cannot read the sender's name directly, but we can weigh the envelope with exquisite care, and if it weighs even slightly more than the known contents allow, we know there is something extra inside. For a particle that arrived with no job and no explanation, the muon turned out to hold one of the most consequential quantities anyone could measure. It helps to be honest about the scale of what we're comparing. The anomaly is roughly 1 part in 800, dominated by Schwinger's simple term. But the disagreement physicists were chasing was not in that first digit. It was buried far deeper, around the 8th or 9th decimal place of the magnet, a difference of a few parts in 10 billion. To even speak of such a gap, Both the measurement and the calculation have to be controlled to better than a part in a billion. This is among the most demanding comparisons in all of science. Theory and experiment each push to absurd precision, meeting at a single faint number and asking whether they agree. For decades, the measurement side and the theory side advanced together, each refining its tools, each adding digits, circling toward the moment they could be laid side by side with real confidence. When that moment came, they did not match. The measured magnet came out persistently a touch stronger than the known particles seemed able to explain. The gap was small, but it would not go away, and it was large enough to matter. That stubborn little gap is the quiet panic of our title, but a comparison has two sides, and a gap can come from either one. Before we can trust that the Muon is telling us about new particles, we have to understand how each side is actually built, starting with the breathtaking machine that measures the magnet by watching muons run in circles. To measure the muon's magnet, you do not weigh it or probe it directly. You let muons run in a circle and watch their spins drift. The whole method rests on a small lucky gap between two motions, and once you see that gap, the giant rings of this story make perfect sense. Picture a single muon launched into a large ring, held on its circular path by a strong magnetic field, looping around and around like a runner on a circular track. The muon has two things going on at once. Its body, so to speak, sweeps around the ring, its direction of motion turning steadily as it follows the curve, and its spin, the little internal arrow that makes it a magnet, also wheels around, processing in the same magnetic field the way we described earlier. Two rotations, happening together, the motion around the track and the spins wheeling. Here is the crucial point. If the muon's g-factor were exactly 2, those two rotations would stay perfectly in step. The spin arrow would turn at precisely the same rate as the direction of motion, so the muon would always point the same way relative to its travel, like a runner who keeps facing exactly along the track at every moment. There would be nothing to see. The spin and the motion would wheel around together in lockstep, lap after lap, revealing nothing about any anomaly. But the g-factor is not exactly 2. It is that sliver more, because of the anomaly. And that sliver means the spin wheels around just slightly faster than the direction of motion. With every lap, the spin gets a tiny bit ahead, drifting forward relative to the muon's travel, like a runner who slowly rotates to face a little more inward with each circuit, until, over many laps, they have turned all the way around relative to the track. The rate of that slow, extra drift, the gap between the spins wheeling and the motions turning, depends only on the anomaly. It is, in the most direct possible way, the magnet's excess made visible as a slow turning. This is the beautiful trick at the centre of every muon magnet experiment, and it is why they're called G-2 experiments. They do not measure G. They measure the small difference, G-2, by watching the slow drift of the spin against the motion. Everything irrelevant cancels out, and what remains is the anomaly itself, expressed as a frequency, a number of drifts per second. Measure that frequency, measure the magnetic field, and you can extract the anomaly to staggering precision. The everyday way to feel this is 2 clocks running at almost the same speed. If 2 clocks tick at exactly the same rate, you learn nothing by watching them, since their hands stay together forever. But if one runs ever so slightly fast, then over hours the fast one creeps ahead, and by watching the slowly growing gap between the two, you can measure that tiny difference in rate with great accuracy. The muon's motion is 1 clock, its spin is the other, and the anomaly is the faint difference in their rates that you read off from the drift. The comparison is rough, because clocks do not spin or carry charge, but it captures why a small difference becomes measurable when you let it accumulate over many laps, so the experiment becomes clear in outline. Make a great many muons, all spinning the same way, inject them into a ring and hold them there with a magnetic field. Watch how their spins drift relative to their motion, lap after lap, and read the anomaly from the rate of that drift. Simple to state, brutally hard to do. And there is a deep problem hiding in it. because holding the muons in a tight beam requires electric fields too, and electric fields disturb the very spin you're trying to watch. The solution to that problem is a single, almost magical choice of speed. The problem is this: to keep muons circling in a tight, well-behaved beam inside the ring, a magnetic field alone is not enough. The beam tends to spread, drifting up and down, and you need something to squeeze it back, to focus it the way a lens focuses light. The natural tool for that is an electric field, but an electric field, like a magnetic one, tugs on the muon's spin, adding its own twist to the precession. That extra twist would corrupt the very drift you're trying to measure, mixing in a contribution that has nothing to do with the anomaly. Focus the beam, and you spoil the measurement. It seems like a trap. There is a way out, and it is one of the most elegant tricks in experimental physics. It turns out that the disturbing effect of an electric field on the spin depends on how fast the muon is moving. At low speeds, the electric field twists the spin strongly. At higher speeds, the twist weakens, and at one particular, special speed, the unwanted twist from the electric field vanishes entirely. The electric field still focuses the beam, still squeezes the muons into a tidy stream, but its effect on the precession cancels out perfectly, leaving the spin to drift only because of the magnetic field and the anomaly, exactly as you want. That special speed corresponds to a particular energy, and the energy has a value physicists know by heart. It is about 3.1 giga-electron volts, a unit of energy used for particles, and at this energy the muon is moving so fast that its internal clock runs at about 29 times slower than a muon at rest. Physicists call this the magic momentum, and the name is sincere. There is no deep cosmic reason the cancellation happens at that exact speed. It falls out of the way the equations balance, a genuine gift from the mathematics, and the experiments are built around it. The magic momentum does a second favour at the same time, and it ties back to an earlier chapter. Remember that a muon at rest lives only about 2 millionths of a second, far too short to run many laps of a large ring. At the magic momentum, with the muon's clock slowed by that factor of about 29, its life stretches to around 64 millionths of a second as seen from the laboratory. That is still a flicker by human standards, but it is long enough for the muon to complete hundreds of laps of the ring before it decays, and hundreds of laps is exactly what you need to watch. The slow drift of the spin accumulate, the same relativity that lets atmospheric muons reach the ground, lets laboratory muons live long enough to be measured. To create the focusing electric field at the magic momentum, the experiments use devices called electrostatic quadrupoles, sets of charged plates arranged around the beam that gently push wandering muons back toward the centre, like soft walls keeping the stream on course. They squeeze the beam vertically without, thanks to the magic speed, disturbing the spin's drift. It is a careful balance, holding the muons in tightly, while leaving the one quantity you care about untouched. So the design tightens further, make muons, accelerate them to precisely the magic momentum of about 3.1 giga-electron volts, inject them into the ring, hold them with a magnetic field and focus them with electric quadrupoles, and watch the spin drift that reveals the anomaly. The relativistic stretching of time, the magic momentum cancellation, and the focusing fields all work together in one machine. But one enormous practical question remains, and it is not obvious there is any answer at all. The muons are sealed inside the ring, looping invisibly. How can anyone possibly see which way each muon's spin is pointing, lap after lap, in order to track its drift? The muon would have to somehow announce its own orientation. Remarkably, it does exactly that, and the reason reaches into one of the deepest and strangest asymmetries in all of nature. The muons are sealed inside the ring, looping invisibly in the dark, and somehow the experiment must know which way each one's spin is pointing in order to track its slow drift. The muon solves this problem itself. When it dies, it tells you, in the only language it has, exactly which way it was facing. Recall that a muon decays into an electron and two neutrinos, or for the positively charged muons usually studied into a positron and two neutrinos. The crucial fact is that this decay is not even-handed about direction. The positron does not fly off randomly. It comes out preferentially along the direction the muon's spin was pointing, like an arrow released from a bow that was aimed. Catch the positron, note which way it went, and you have learned where the muon's spin was at the moment it broke apart. The muon announces its own orientation by the direction in which it throws its decay. This lopsidedness runs against an assumption physicists held for a long time, that nature has no preference between left and right, that the laws of physics would look the same in a mirror. For most of physics this is true, but in 1956 two theorists, Tsung-Dao Lee and Chen-Ning Yang, suggested that the weak force, the same force responsible for this kind of decay, might secretly tell left from right. Within months, the physicist Qianxing Wu confirmed it in a careful experiment with cooled radioactive cobalt, and almost at once Richard Garwin, Leon Lederman, and Marcel Weinrich confirmed it directly in muon decay. The muon, it turned out, decays with a built-in handedness. Nature does know its left from its right after all, and the muon wears that asymmetry on its sleeve. This is the deep reason the whole measurement is possible, and it is the part most retellings hurry past. Without this handedness, a decaying muon would scatter its positrons evenly in all directions, and you could never read its spin. Because of it, the positrons lean toward the spin, and the muon becomes self-reporting. The experiment does not need to reach inside and check each muon. It only needs to wait for the muon to die and to notice which way the final positron flew. Now picture the ring in action. Detectors line the inner edge of the circle, ready to catch positrons. As the muons loop around, their spins are all wheeling together, drifting slowly ahead of their motion because of the anomaly. When the spins, as a group, point toward the detectors, more positrons come flying inward, and the detectors counter surge. A moment later, as the spins drift around to point the other way, fewer positrons reach the detectors and the count falls. The number of positrons striking the detectors rises and falls, over and over, in a steady beat. If you plot that count against time, you see a curve that ripples up and down, a wave riding on a slow downward slope. The slope comes from the muons gradually decaying away, the whole population thinning as time passes, just as we described. The ripple on top comes from the spin and drifting around and around, sweeping past the detectors again and again. Physicists call this the wiggle plot, and the speed of the wiggle is precisely the drift frequency, the anomaly made visible. Measure how fast the wiggle ripples, measure the magnetic field that drives it, and the muon's anomaly falls out. It is a remarkable closing of the circle. The muon's brief life, which seemed at first like a nuisance, becomes the very thing that delivers the measurement, because each death sends out a positron that points the way. The particle that nobody ordered measures itself by dying in a slightly crooked direction. With this last piece in hand, the experiment is complete in principle, and physicists could finally build real machines to read the number. The first of them rose at a laboratory in Europe. The first serious attempts to measure the muon's anomaly were made at CERN, the European laboratory near Geneva, beginning in the late 1950s and stretching across the 1960s and into the 70s. Over 3 successive experiments, each more refined than the last, the physicists there turned the elegant idea of the wiggle plot into hard numbers, and in doing so they tested the theory of the restless vacuum more sharply than anyone had before. The early CERN work was modest by later standards, but bold for its time. The first experiment did not even use a full ring. It sent muons down a long straight magnet, watching their spins drift as they travelled, and managed to confirm that the muon's anomaly was close to the value Schwinger's simple term predicted. That alone was an achievement. It showed that the muon, like the electron, carried a magnet slightly stronger than the clean value of 2, and that the excess came from the vacuum's flickers, just as quantum electrodynamics said it should. The later CERN experiments built true storage rings and pushed the precision much further, down to a few parts in a million. At that level, something important came into view. The measurement was now sharp enough that the simple flickers of light and electrons could no longer account for the whole anomaly. There was a small additional contribution, and it came from heavier flickers, from virtual particles that feel the strong nuclear force. The CERN measurements were the first to feel, in the muon's magnet, the faint tug of these hadronic flickers. The vacuum around the muon was proving to contain more than light alone, exactly the richness we will need to reckon with later. This is worth pausing on, because it foreshadows the entire later drama. As soon as the measurement grew precise enough, the hardest part of the theory, the contribution of the strongly interacting particles became unavoidable. CERN's physicists could see its effect but could only roughly predict its size. For the moment, the agreement between measurement and theory held within the uncertainties of the day, and that agreement was itself a triumph. Quantum electrodynamics and the broader picture of the vacuum were passing a demanding test. The CERN experiments also sharpened the techniques that everything afterward would rely on. They refined the use of the magic momentum, the special speed at which the focusing electric fields leave the spin's drift untouched. They improved the detectors that caught the decay positrons and traced the wiggle. They learned how to make intense, clean beams of muons all spinning the same way, and how to inject them into a ring and hold them there for hundreds of laps. The playbook for measuring the anomaly was written, in large part, at Geneva. By the time the CERN program wound down in the late 1970s, the muon's anomaly was known to about 10 parts in a million, and it agreed with theory. For many that might have seemed enough. The number was measured, the theory matched, the case looked closed. But a few parts in a million, while impressive, was not fine enough to feel the faintest possible visitors in the vacuum. If some new and heavy particle were flickering around the muon, leaving a thumbprint smaller than the current uncertainty, the CERN experiments would have walked right past it without noticing. To go further meant going to even greater precision, by a large factor, and that required a new and even more ambitious machine. The work moved across the Atlantic to a laboratory on Long Island, where physicists set out to build the most precise muon ring yet, and to ask, with new sharpness, whether the measured magnet truly matched the calculated one. It was there that the first real crack appeared. At Brookhaven National Laboratory, on Long Island in New York, physicists set out in the 1990s to measure the muon's anomaly far more precisely than CERN ever had. The centerpiece of their experiment, known by its catalogue name E821, was a superconducting storage ring about 50 feet across, a great circular magnet built to hold muons on their looping path with a field of extraordinary steadiness. This ring is the same one that will travel across the country later in our story, so it is worth picturing now. A circle of magnet roughly the width of a comfortable house, cooled to keep its coils superconducting, with muons racing around its rim. The goal was to push the measurement of the anomaly down to better than 1 part in a million, sharp enough to feel contributions to the muon's magnet that the CERN experiments could not. The team made beams of muons all spinning the same way, injected them into the ring at the magic momentum, focused them with electrostatic plates, and watched the wiggle of decay positrons climb and fall as the spins drifted. They gathered data through the late 1990s and into the early 2000s, refining the number with each run. When they compared their measured anomaly to the best theoretical prediction of the time, the two did not quite match. The measured magnet came out slightly stronger than the known particles seemed able to explain. The gap was tiny, far down in the digits, but it was persistent, and as the Brookhaven team gathered more data, the gap held its ground rather than melting away. By the time the experiment published its final results in the mid-2000s, the disagreement stood at a little more than 3 standard deviations. We will look closely at what that phrase means in a later chapter, but the rough sense is this. A gap of 3 standard deviations is large enough to take seriously and too small to trust completely. It is the size of result that makes physicists lean forward without yet letting themselves believe. It might be the first sign of a new particle flickering in the muon's cloak. It might also be a subtle flaw in the measurement, or in the difficult theoretical prediction. or simply an unlucky statistical fluctuation that more data would wash away. 3 standard deviations is a knock at the door that may or may not be someone there. The Brookhaven result was tantalizing precisely because of where it sat. Had the measured and predicted magnets agreed perfectly, the story would have ended quietly, with the known particles confirmed as the whole cast. Had the gap been enormous and unmistakable, it would have been a clear discovery of something new. Instead, it landed in the uneasy middle, a gap big enough to hint at new physics but small enough that no one could be sure. That uneasy middle is where the Muon's magnet would sit for years, and it is the source of the quiet panic in our title. The result demanded a response. A 3 standard deviation gap cannot be left hanging. Either the measurement had to be sharpened until the gap became undeniable or dissolved, or the theory had to be tightened until everyone trusted the prediction it was being compared against. Both efforts began. The experimental side needed a more precise machine, and building one from scratch would have taken many years and enormous money. But there was a faster way. A perfectly good ring already existed, the very one at Brookhaven, and a more powerful Muon beam was available at another laboratory 1,000 miles away. All that stood between them was the small matter of moving a 50-foot superconducting magnet across the eastern United States. In the summer of 2013, the most unusual cargo on the American roads was a single 50-foot ring of superconducting magnet, wrapped in protective covering, riding a specially built trailer at a walking pace through the night. It was the Brookhaven storage ring, on its way to a new home at Fermilab, the great particle physics laboratory outside Chicago, where a more intense beam of muons waited. The journey would cover about 3,200 miles and would become, briefly, a piece of public theatre. The reason for the move was practical. Building a new ring of that size and quality would have cost a fortune and taken many years, while the Brookhaven ring already existed and already worked. Fermilab, meanwhile, could deliver a far purer and more plentiful beam of muons than Brookhaven ever could, which meant more data and a sharper measurement. The sensible thing was to bring the ring to the beam. The catch was that the ring could not be taken apart. Its large superconducting coils, the heart of the magnet, could not be bent or twisted by more than a tiny amount without ruining them forever. The whole circle, fragile and enormous, had to travel in one piece, kept almost perfectly flat and barely flexed. So the engineers built a special fixture to hold the ring rigid, loaded it onto a custom trailer, and planned a route that avoided sharp turns and rough ground. Trucks cannot easily carry a load 50 feet wide through ordinary highways, so for most of the trip the ring went by water. It was floated onto a barge at Long Island, carried down the Atlantic coast, around the tip of Florida, into the Gulf, and up the rivers of the American interior toward Illinois. Only the first and last stretches went by road, slowly, at night, on a truck creeping along closed lanes. The slow road portions drew crowds. People came out to the roadsides to watch the strange white circle drift past in the dark, escorted by police and engineers, moving slower than a person walks. The laboratory had asked the public to follow along, and many did, tracking the ring's progress and gathering to see it pass through their towns. For a few weeks, an obscure piece of physics equipment became a minor celebrity, a giant ring on a flatbed, and a great many people who would never read a physics paper got to stand at the curb and watch a real scientific instrument go by. The trip took about 5 weeks, and the ring arrived in Illinois intact, its delicate coils unharmed. There is something fitting in this image, and it rewards a moment's thought. The whole point of the ring is to measure a number buried in the 11th digit of a particle's magnet, a quantity of almost unimaginable subtlety. And to do it, human beings had to physically haul a 50-foot magnet 3,000 miles by sea and road, babying it the entire way so that not one coil flexed too far. The extreme delicacy of the measurement and the brute physical labour of the move sit side by side. 2 faces of the same effort to read what the muon has to say. Arriving at Fermilab was only the beginning. A ring that works at one laboratory does not simply switch on at another. The magnet had to be reassembled, powered up, and then coaxed into producing a field of staggering uniformity, far steadier than it had ever needed to be at Brookhaven. New detectors had to be built and installed. The Muon beam had to be tuned and threaded into the ring. Years of painstaking work lay ahead before the rebuilt machine could deliver a single trustworthy number. That work is where the modern measurement was truly made. A storage ring that has just been moved across a continent does not produce good physics on arrival. It produces a long list of problems. At Fermilab, the team spent years turning the relocated Brookhaven ring into an instrument far more precise than it had ever been, and most of that work came down to two demands. The magnetic field had to be made astonishingly uniform, and the muons had to be tracked with new and better eyes. Consider the magnetic field first, because the whole measurement leans on it. To extract the anomaly, you measure how fast the muon spin drifts, and you measure the strength of the magnetic field that drives that drift, and you compare the two. If the field is even slightly different in one part of the ring than another, the muons will feel different pushes at different points in their laps, and the measurement blurs. So the field, of about 1.5 Tesla, thousands of times stronger than a refrigerator magnet, had to be made the same all the way around the ring to a few parts in a million. Achieving that meant a painstaking process called shimming, placing thousands of tiny pieces of metal foil around the ring by hand, each one nudging the field a hair closer to perfect evenness, until the great circle held a field of almost eerie uniformity. The field also had to be measured constantly while the experiment ran, because it could drift with temperature and time. The team used precise probes based on the same physics as a hospital magnetic scanner, mapping the field throughout the ring and watching it moment to moment. In the end, they knew the magnetic field that the muons felt to better than a part in 10 million, an accuracy that took years of effort to reach and hold. Then there were the detectors that catch the decay positrons and build the wiggle plot. Fermilab installed new calorimeters, blocks of special crystal that flash with light when a positron strikes them, recording both when each positron arrives and how much energy it carries. They added delicate trackers inside the vacuum of the ring, arrays of thin straws that map the exact paths of positrons curling out from the beam. Together, these let the team reconstruct the wiggle with far more detail than before, and to hunt down the small systematic effects that could fool a less careful experiment. Over all of this hung a discipline meant to protect the physicists from themselves, called blinding. When you're chasing a number in the 11th digit, knowing what answer you hope to find is dangerous, because hope can quietly bias 1,000 small choices in the analysis. To guard against it, the team hid the answer from themselves. The master clock that timed the wiggle was deliberately set to a secret, slightly wrong frequency, an offset sealed in envelopes and known to no one on the analysis teams. Every group analysed the data without knowing the true scale, so no one could nudge the result toward a favoured value. Only at the very end, in a formal ceremony, were the envelopes opened and the true frequency revealed, and the real answer emerged for the first time. That moment of unblinding is one of the genuinely dramatic rituals of modern physics. Years of work by hundreds of people come down to a single number that no one has been allowed to see, finally written on the board in front of the whole collaboration. There is no taking it back and no quiet adjustment afterward. Whatever the muons have said, that is the answer. When the Fermilab team finally opened their envelopes and applied the true frequency, the number that appeared was sharper than Brookhaven's, and it told the same story. The gap was still there. The announcement of that result in 2021 is where the quiet unease became loud. In April of 2021, the Fermilab team announced its first measurement of the muon's anomaly, and for a few days a subtle quantity buried in the 11th digit of a particle's magnet was front-page news around the world. The headline was simple. The new sharper measurement agreed with the old Brookhaven result, and together they disagreed with the theoretical prediction. The muon's magnet was stronger than the known particles seemed able to explain. The Fermilab number, drawn from its first run of data, landed almost exactly where Brookhaven's had, but with greater precision. That agreement mattered enormously. when two different teams using the same ring but rebuilt, with new detectors, new methods, and a new and more intense beam, arrive at the same slightly anomalous value, it becomes much harder to blame the result on a quirk of one machine. Two independent looks had now seen the same gap. Combined, the Brookhaven and Fermilab measurements disagreed with the prediction of the time by about 4.2 standard deviations. That figure, 4.2, was repeated everywhere, and it carried real weight. It was larger than Brookhaven's gap had been, pushed up by the new data, and it sat close to the threshold physicists used to take a result very seriously indeed. The story told in the press was thrilling and almost irresistible. The Muon, that heavy and sensitive listener, seemed to be feeling the tug of something not in our list of particles, some new force or new piece of matter flickering in the vacuum around it. After decades of a standard model that stubbornly explained everything, here, perhaps, was the first solid crack, the first direct sign of physics beyond it. The excitement was not foolish. This was exactly the situation the whole effort had been built to reach. The Muon's magnet had been chosen as a probe precisely because a gap between measurement and prediction could signal new particles, and now there was a gap, confirmed by two experiments, sitting at a tantalizing size. If it held and grew, it would be among the most important findings in physics in half a century, a genuine doorway out of the standard model and into something larger. But the more careful physicists, including many on the experiment itself, were measured in their language, and their caution is the heart of this chapter. A gap of 4.2 standard deviations is striking, but it is not the level the field demands before declaring a discovery. The history of physics is dotted with anomalies of just this size that glowed brightly for a year or two, and then faded as more data came in, revealed to be statistical flukes or subtle mistakes. Experienced researchers had seen such ghosts before, and they knew better than to celebrate too early. They allowed themselves to be intrigued, not convinced. There was also a deeper reason for caution, one that often got lost in the headlines. The gap is the difference between two numbers, the measured magnet and the predicted magnet. The measurement was now superb and getting better, but the prediction, the theoretical value the measurement was being compared against, was itself an enormous and difficult calculation, and not everyone agreed on what it should be. A gap can open up because the measurement has found something new. It can also open up because the prediction is slightly off, and in this case, troublingly, there was already reason to wonder whether the prediction everyone was comparing against could be fully trusted. So even at the height of the excitement, the real situation was subtler than the headlines suggested. To understand whether the Muon was truly pointing to new physics, one had to understand both halves of the comparison with equal care. Before we follow the theory side into its difficulties, it is worth slowing down to understand exactly what a number like 4.2 standard deviations does and does not mean, because that single phrase governs how the whole field reads a result like this. The phrase 4.2 standard deviation sounds technical, and it governs how physicists react to a result like the muons, so it is worth understanding in plain terms. At heart, it is a way of answering one question. If there were really no new effect at all, how surprising would it be to see a gap this large purely by chance? Every measurement carries noise. Measure anything many times and the answers scatter a little around the true value, high one time, low the next, like arrows landing in a loose cluster around the bullseye. The spread of that scatter is captured by a quantity called the standard deviation, often written with the Greek letter sigma. 1 sigma is the typical size of the random wobble. So when physicists say the muon's gap is 4.2 sigma, they mean the gap is 4.2 times larger than the natural wobble of the measurement. It is the size of a result that random noise would rarely produce on its own. How rarely depends steeply on the number of sigma, and the steepness is the key. A gap of 1 sigma is nothing, the sort of thing chance throws up constantly. A gap of 2 sigma happens by luck a few % of the time, often enough to ignore. By 3 sigma, the odds of a pure fluke have dropped to a fraction of a %, and physicists start paying attention, calling it evidence. By 5 sigma, the chance of the result being a random accident falls to about 1 in 3.5 million, and only at that point does the field allow the word discovery. 5 sigma is the gold standard, the line a result must cross before physicists will say they have truly found something. 4.2 sigma, then, sits in a meaningful but uncomfortable place. It is well past the threshold for evidence, and well short of the threshold for discovery. The odds of so large a gap arising from pure chance are small, perhaps a few in 100,000, small enough that most physicists doubt it is simple bad luck. And yet the field has learned, through hard experience, not to trust even a 4 sigma result fully, because a fluke is not the only way a false signal can appear. This is where the caution earns its keep, and the history is sobering. Physics has seen a long parade of promising anomalies at 3 or 4 sigma that later vanished. There was a bump in the data at the Large Hadron Collider that looked for a while like a brand new particle and then evaporated as more data arrived. There was a famous measurement that seemed to show particles travelling faster than light, which turned out to be a loose cable in the timing system. Time and again, results that looked tantalising dissolved on closer inspection, not because anyone was careless, but because rare flukes and subtle errors are exactly what a 4 sigma effect can be. Burned often enough, the field grew disciplined about waiting for 5. There is a further subtlety that applies with special force to the muon, and it goes beyond the question of flukes. The number of sigma tells you how unlikely the gap is to come from random noise in the measurement. It says nothing about whether the prediction you are comparing against is correct. If the theoretical value is itself slightly wrong, a large gap can open up that has nothing to do with chance and nothing to do with new particles. It is simply the measurement disagreeing with a flawed prediction. Sigma counts the noise in the experiment. It cannot count a mistake in the theory. That is precisely the trap the muon's gap turned out to be sitting near. The 4.2 standard deviations were real, in the sense that the measurement was solid and the gap was not a fluke of noise. But the prediction on the other side was about to be called into serious question. Before we follow that thread, it helps to look at what physicists were hoping the gap might be, the new and exotic particles that could, if the gap were genuine, be flickering in the muon's cloak. Suppose for a moment that the gap is real. Suppose the muon's magnet truly is stronger than all the known particles can account for, and the difference is the fingerprint of something new flickering in the vacuum around it. What could that something be? For years, physicists drew up lists of suspects, and the candidates reveal what the muon's anomaly was thought capable of detecting. The most celebrated suspect was a sweeping idea called supersymmetry. The known particles of nature fall into 2 broad kinds, the matter particles like the electron and the muon, and the force-carrying particles like the photon of light. Supersymmetry proposes that every known particle has a heavier, undiscovered partner of the other kind, a hidden mirror roster of new particles waiting to be found. If these partners exist, some of them would flicker in the cloak around the muon, and their presence would shift its magnet by a small amount. For decades, supersymmetry was the leading hope for physics beyond the standard model, partly because it could neatly explain several puzzles at once, and a muon anomaly of about the observed size was just what many versions of it predicted. To many, the gap looked like supersymmetry finally making itself felt. A second class of suspect went by the name leptoquark, a hypothetical particle that would do something the known particles never do, directly linking the leptons, like the muon, to the quarks that make up protons and neutrons. Normally, those 2 families keep to themselves. A leptoquark would bridge them, and if one existed, it could flicker around the muon and tug on its magnet. Leptoquarks had also been invoked to explain other small anomalies seen elsewhere, in the decays of certain heavy particles, which made the idea doubly attractive. Perhaps a single new bridge particle was behind several puzzles, the muons among them. A third suspect was lighter and stranger, a new force-carrying particle sometimes called a dark photon. The ordinary photon carries the familiar electromagnetic force. A dark photon would carry a new feeble force, a fifth force beyond the four we know, coupling very weakly to ordinary matter. Even a weak new force, if it existed, would leave a small imprint on the muon's magnet as its carrier flickered in the cloak. The dark photon was especially interesting because such a particle might also have something to do with dark matter, the unseen stuff that outweighs all the visible matter in the universe, tying the muon's tiny anomaly to one of the largest mysteries in cosmology. What unites these suspects is the logic we built earlier. The muon's magnet is sensitive, through the mass-squared rule, to heavy particles flickering around it, including ones we have never made directly. A gap of the observed size pointed to new particles at energies that our biggest accelerators were straining to reach, just out of direct view, but perhaps already whispering through the muon. That was the dream. The muon would be the first to feel particles too heavy or too shy to produce in a collider, sensing them indirectly through the faint shift they left on its magnet. It would be a discovery made not by seeing the new thing, but by feeling its shadow. The dream was real and worth taking seriously, and a great deal of theoretical work went into it. But every one of these suspects rested on the same assumption, that the gap itself was real, that the measured magnet genuinely differed from what the known particles produce, and the only way to know that is to be certain of the prediction, the calculated value of the magnet using the known particles alone. If that prediction was wrong, the gap could be an illusion, and the suspects would all have alibis. So the question of new physics turns, in the end, on a question of arithmetic. How well can we actually calculate what the muon's magnet should be? The gap that excited everyone is a difference between two numbers, and we have spent many chapters on only one of them, the measured magnet read from the wiggle in the ring. The other number, the predicted magnet, is just as hard won, and the entire question of new physics depends on trusting it. So we now turn fully to the theory side, to the monumental calculation of what the muon's magnet should be if only the known particles exist. The reason this matters cannot be overstated. A gap can open for two completely different reasons. It can open because the measurement has detected something genuinely new, a particle missing from our list. Or it can open because the prediction is slightly wrong, so that the measurement is simply disagreeing with a flawed calculation rather than with nature. From the outside, the two look identical. Both produce a number that does not match. The only way to tell them apart is to be as sure of the prediction as you are of the measurement, and that turns out to be extraordinarily demanding. To predict the muon's magnet, you must account for every kind of flicker that can happen in the cloak around it, every virtual particle that can briefly appear and tug on the spin. Each type of flicker contributes its own small shift to the anomaly, and to match the precision of the measurement you must compute all of them, large and small, down to a part in a billion or better. It is a calculation assembled from many separate pieces, each demanding in its own way, and the final prediction is only as trustworthy as its weakest part. Physicists sought these contributions by which forces at work in the flicker. The largest by far come from the electromagnetic flickers, the muon emitting and reabsorbing light and light electrons, governed by quantum electrodynamics. A much smaller set comes from the weak nuclear force, involving the heavy particles that carry it, and a third set, troublesome out of all proportion to its size, comes from the strong nuclear force, involving quarks and the particles built from them. The electromagnetic and weak pieces, as we'll see, are under beautiful control. The strong force piece is where the whole prediction becomes uncertain, and where the real action of the modern story lies. To manage so vast a calculation, the world's experts in this corner of physics organised themselves into a single group, the Muon G2 Theory Initiative. Its purpose was to bring together everyone working on the prediction, compare their methods, resolve their differences, and produce one agreed-upon value for the muon's magnet, complete with an honest estimate of its uncertainty. This consensus number would be the official prediction, the one the experimental result would be measured against. In 2020, the initiative published its first such consensus, a detailed document arrived at by many hands, and it was this prediction that the Fermilab measurement disagreed with by 4.2 standard deviations. So when the headlines announced a gap, they were announcing a disagreement between the new measurement and this carefully assembled consensus prediction. The prediction was the product of years of work by many of the best people in the field, which is why the gap was taken so seriously. And yet, even as that consensus was published, a crack was forming inside it. One of the pieces of the calculation, the troublesome strong force piece, could be computed in two very different ways, and the two ways were beginning to disagree with each other. To see why that disagreement would eventually overturn the whole story, we have to look at how the prediction is built, starting with the parts that work almost perfectly. Most of the predicted magnet rests on solid ground, and it is worth appreciating just how solid, because it sharpens where the trouble actually lies. By far the largest part of the Muon's anomaly, and the most precisely calculated, comes from quantum electrodynamics, the theory of charged particles and light that we met earlier. This is the part physicists can compute almost as far as they please. Recall that the simplest flicker, the muon briefly emitting and reabsorbing a single particle of light, was what Schwinger calculated, giving the term alpha over 2 pi. But that is only the first and largest of an endless series. There are flickers with 2 particles of light involved, and flickers with 3 and 4 and 5, each more intricate than the last, each contributing a smaller correction to the magnet. To compute them, physicists draw and evaluate the Feynman diagrams for every possible way the flickers can happen, and the number of diagrams explodes as you go deeper. The scale of this effort is hard to grasp. The first level has 1 diagram, Schwinger's, the next has a handful. But by the 5th level of complexity, the level physicists have actually computed for the muon. The number of distinct diagrams climbs past 12,000. Each diagram is a separate, often brutally difficult piece of arithmetic, and many cannot be done by hand at all. The physicist Toichiro Kinoshita devoted much of a long career to this calculation, developing methods to evaluate the towering stacks of diagrams by computer, level upon level, over decades of work. The result is that the electromagnetic contribution to the muon's magnet is known to an almost absurd precision, far finer than the experiment can even test. This is one of the quiet wonders of physics, and it deserves a plain statement. Using nothing but theory, by drawing and computing thousands of little diagrams of flickering light, physicists can predict a particle's magnet to 10 or more decimal places, and when the same calculation is done for the electron and checked against the electron's exquisitely measured magnet, theory and measurement agree to a precision like measuring the distance between 2 cities and being wrong by less than the width of a single human hair. Quantum electrodynamics is the most accurately tested idea in the history of science, and its contribution to the muon's magnet is rock solid. There is a second contribution, smaller and also well controlled, from the weak nuclear force. This force is carried by heavy particles, the ones responsible for certain kinds of radioactive decay, along with the Higgs particle that gives mass to the others. These heavy carriers can flicker in the muon's cloak too, and because they are heavy, the mass-squared sensitivity gives them a real if modest effect. The weak contribution to the muon's magnet is tiny, a small fraction of the whole anomaly, but it is firmly calculated because the weak force, like the electromagnetic one, can be handled with the orderly diagram-by-diagram method. The known particles that carry it are well understood, and their flickers add up to a number physicists trust. So 2 of the 3 contributions to the prediction are in excellent shape. The electromagnetic piece is enormous and known to staggering precision. The weak piece is small and well controlled. If these were the whole story, the predicted magnet would be as trustworthy as the measured one, the comparison would be clean, and a gap between them would point straight at new physics with little room for doubt. But they are not the whole story. There remains the third contribution, from the strong nuclear force, and although it is far smaller than the electromagnetic piece, it carries by far the largest uncertainty. It is the single piece of the prediction that physicists cannot compute cleanly, the place where the orderly method of diagrams breaks down, and therefore the place where the entire question of the gap is truly decided. To understand the muon's mystery, we have to understand why the strong force is so hard. The third contribution to the muon's magnet comes from the strong nuclear force, and it is the troublemaker of the whole calculation. It is far smaller than the electromagnetic part, contributing only a modest slice of the anomaly, yet it carries the largest uncertainty by a wide margin, and that uncertainty dominates the entire prediction. To see why, we have to understand what makes the strong force so different from the others. The strong force is what binds quarks together into particles like the proton and the neutron, and binds those together into atomic nuclei. It is carried by particles called gluons, and it is the most powerful of nature's forces at short range. Its defining strangeness is that it does not weaken with closeness the way the others do, and at the low energies relevant here it is so strong that the tidy method of Feynman diagrams simply fails. For the electromagnetic force, each successive flicker is smaller than the last, because the force is feeble enough that adding more particles of light makes ever tinier corrections. The series settles down and can be summed. For the strong force at these energies, the opposite happens. The flickers do not shrink as you add more, so there is no orderly series to sum. The whole diagram by diagram approach, which works so beautifully for light, collapses. This is the crux of the difficulty. When a muon's cloak includes a flicker involving the strong force, that flicker is not a clean single event but a roiling tangle of quarks and gluons, a brief storm of the strongly interacting particles, impossible to capture by adding up a handful of diagrams. The strong force contribution to the magnet is real and must be included to match the precision of the measurement, but it cannot be calculated by the method that tames the other forces. Some other way is needed. The dominant piece of this strong force contribution has a name worth knowing, because it sits at the centre of everything that follows. It is called the hadronic vacuum polarization, often shortened to its initials. The picture behind the name is this. The muon briefly emits a particle of light, and that particle of light, in its own fleeting moment, turns into a swarm of strongly interacting particles, quarks, and their kin, which then recombine before the light is reabsorbed by the muon. That brief detour through the strong force swarm, the light momentarily becoming a storm of quarks, is the hadronic vacuum polarization, and it is the single largest source of uncertainty in the entire predicted magnet. There is a second, smaller strong force piece as well, with its own forbidding name, the hadronic light-by-light contribution, in which several particles of light interact through a tangle of quarks all at once. It is harder still to picture and harder to compute, but it is smaller, and for most of this story the larger hadronic vacuum polarization is the piece that matters most. It is the one whose uncertainty swamps all the others, and therefore the one that decides whether the gap with experiment is real. Here is the situation stated plainly. The predicted magnet is a sum of pieces. The electromagnetic and weak pieces are known with great confidence. The strong force pieces, especially the hadronic vacuum polarization, are known far less well, and their uncertainty is large enough to govern whether the measured magnet truly disagrees with the prediction. If the strong force piece is one value, the gap is real and points to new physics. If it is another value, the gap shrinks or vanishes, and there is nothing to explain. Everything hinges on getting this one stubborn number right. Since the diagram method fails, physicists develop two completely different ways to pin down the hadronic vacuum polarization. One uses real experimental data as a stand-in. The other simulates the strong force directly on supercomputers. For years they were thought to agree. When they were finally compared with full precision, they did not, and that disagreement is where the Muon story takes its sharpest turn. The first way to pin down the troublesome strong force contribution does not try to calculate it from scratch at all. Instead, it borrows the answer from nature, using real experimental data to stand in for the part of the theory we cannot compute. It is an ingenious sidestep, and for decades it was the gold standard. Physicists call it the data-driven method. The trick rests on a deep connection. The hadronic vacuum polarization involves a particle of light briefly turning into a swarm of strongly interacting particles and back again. It happens that this same process, light turning into a swarm of quarks, is something physicists can study directly in a different setting. In a collider, you can smash an electron into its antimatter twin, a positron, and when they annihilate, they produce a flash of light energy that turns into exactly such a swarm of strongly interacting particles. By measuring how often that happens, at many different collision energies, you measure the very same physics that governs the muon's hadronic flicker. So the method works like this. Take decades of data from electron-positron colliders around the world, recording how readily their collisions turn into sprays of strongly interacting particles across a wide range of energies. Then, through a well-established mathematical relationship, convert all that measured data into the value of the hadronic vacuum polarization for the muon's magnet. You're not computing the strong force swarm from theory, which is hopeless. You're measuring its effect in one experiment and importing it into the prediction for another. The strong force never has to be calculated directly. It only has to be observed. This approach drew on an enormous body of experimental work, measurements gathered over many years at colliders in many countries, each contributing data at different energies. Among the most important were measurements of the simplest and most common swarm, in which the light turns into just two particles called pions, the lightest of the strongly interacting particles. This 2-pion channel makes up the largest part of the hadronic vacuum polarization, so getting it right is essential. Several experiments measured it carefully, and for a long time their results agreed well enough to be combined into a single trusted value. When the Muon G2 Theory Initiative published its consensus prediction in 2020, it used this data-driven method for the hadronic vacuum polarization. The resulting prediction was precise, built on real measurements rather than uncertain calculation, and it was this value that the Fermilab measurement disagreed with by 4.2 standard deviations. In other words, the famous gap was a gap between the measured magnet and a prediction whose hardest piece had been supplied by decades of collider data. As long as that data-driven value was correct, the gap stood and the dream of new physics remained alive. But a method that imports its hardest number from experiment is only as good as that experiment. If the collider data were slightly off, or if different collider measurements secretly disagreed, the imported value could be wrong, and with it the whole prediction. For years, this was not thought to be a serious worry, because the data seemed consistent. The data-driven value was treated as reliable, and attention focused on the measurement and on the exciting possibility of new particles. That confidence was about to be shaken from two directions at once. A completely independent way of finding the strong force contribution was maturing, one that did not rely on collider data at all, but simulated the strong force directly on supercomputers, and at the same time, a new and very careful collider measurement of the crucial 2-pion channel was about to disagree sharply with the older data it was meant to confirm. Together, these two developments would pull the rug out from under the simple story of the gap. The first of them, the supercomputer approach, is where we turn next. The second way to find the troublesome strong force contribution takes the opposite approach from the first. Instead of borrowing the answer from experiment, it tries to calculate the strong force directly, from its own fundamental equations, by sheer computational force. The method is called Lattice quantum chromodynamics, and it leans on some of the largest supercomputers on Earth. Quantum chromodynamics is the full theory of the strong force, the rules that govern how quarks and gluons interact. The equations are known exactly. The trouble, as we saw, is that they cannot be solved by the orderly method of adding up diagrams, because at these energies the force is too strong and the flickers do not shrink. So lattice physicists do something drastic. They give up on pencil and paper series entirely and simulate the strong force on a grid. Here is the idea, and it rewards a slow look. Imagine taking a small box of space and a slice of time and dividing it into a fine grid of points, like a three-dimensional checkerboard extended through time. At every point on this lattice, you place the quark and gluon fields, and you let a computer work out how they push and pull on one another according to the exact equations of the strong force. You're building a tiny simulated cube of the universe inside a machine, with the strong force playing out across its grid. From that simulation, you can compute the hadronic flicker that tugs on the muon's magnet directly, without ever borrowing from experiment. The cost of this is staggering. To capture the strong force faithfully, the grid must be fine, with a great many points, and finer grids mean vastly more computation. The calculation must then be repeated at several grid spacings and extrapolated to an imaginary perfect grid with no spacing at all, because only that limit gives the true answer. Each run can occupy a supercomputer for months. For years, the lattice method was too crude to compete, its uncertainty far larger than the data-driven methods, so it sat on the sidelines while the collider data set the standard. That changed in 2021. A group known as the BMW Collaboration, named for the cities where its members worked, Budapest, Marseille, and Wuppertal, published a lattice calculation of the hadronic vacuum polarization that was, for the first time, as precise as the data-driven value. It was a landmark, the product of years of refinement and enormous computing time, and it carried a surprise that would unsettle the whole field. The BMW value did not agree with the data-driven one. It came out higher, and the direction of that difference was exactly the direction that mattered. Recall that the data-driven prediction, used in the 2020 consensus, sat below the measured magnet, leaving the famous gap that hinted at new physics. The BMW lattice value was larger, which pushed the predicted magnet up closer to what the experiment measured. If the BMW number was right, the gap shrank dramatically, perhaps to nothing. The muon might agree with the standard model after all, and the dream of new particles would quietly fold. So by 2021, the field faced a genuine fork. Two independent, respectable methods for the same strong force number gave different answers. The data-driven method, built on decades of collider data, gave a lower value and kept the exciting gap alive. The lattice method, built on direct simulation, gave a higher value and threatened to erase it. Both could not be right. One of these careful, hard-won calculations had to contain a subtle error somewhere, and no one could yet say which. This was a different kind of problem from the one everyone had been chasing. The question was no longer simply whether the muon disagreed with theory. It was whether our two best ways of computing the theory disagreed with each other. That disagreement is the true centre of the modern story. When physicists laid the two values side by side, the disagreement was sharp. The lattice result from the BMW collaboration and the data-driven result from decades of collider measurements differed by about 5 standard deviations. By the very standard we set earlier, 5 sigma is the threshold for a discovery. Here it marked not a discovery of nature, but a collision between two methods, each claiming to compute the same number, each refusing to match the other. Sit with what that means, because it reframes everything. For years, the story had a clean shape. On one side stood the measured magnet, read from the wiggle in the ring. On the other stood the predicted magnet, computed from the known particles. The gap between them was the mystery, and the hope was that it signalled new physics. But that picture quietly assumed the prediction was a single agreed number. It was not. The prediction's hardest piece, the strong force contribution, came in 2 flavours that disagreed with each other more sharply than either disagreed with the experiment. So the mystery moved. It was no longer cleanly a question of the muon against the standard model. It had become a question of one calculation of the standard model against another. If the lattice value was correct, the predicted magnet rose to meet the measurement, the famous gap closed, and the muon turned out to obey the known laws after all. If the data-driven value was correct, the predicted magnet stayed low, the gap held, and the door to new particles remained open. The fate of the new physics dream now hung not on the muon, but on which of 2 arithmetic methods to believe. This is a subtler and in some ways more uncomfortable situation than a simple anomaly. A gap between measurement and prediction is exciting, because it might be nature speaking. A gap between two predictions is unsettling, because it means we do not fully understand our own tools. One of these careful calculations, performed by experts using methods refined over decades, was wrong by an amount large enough to change the conclusion, and the field could not immediately say which. The strong force, the troublemaker from the start, had found a new way to make trouble. There were reasons one might lean either way, and honest physicists felt the pull of both. The data-driven method had the weight of history and a vast body of real measurements behind it. It was hard to believe that decades of collider experiments, cross-checked across many laboratories, could be collectively off by enough to matter. On the other side, the lattice method relied on none of that data. It computed the strong force from first principles, and it had now reached a precision its earlier versions never had. Other lattice groups, checking pieces of the calculation, were beginning to lean in the same direction as BMW. Both methods had earned trust, and that was exactly the problem. What the field needed was a way to break the tie, some independent check that could tell which value was closer to the truth. Two possibilities stood out. More lattice groups could perform the full calculation independently, with their own methods and their own blinding, to see whether they confirmed the high BMW value or not. And the collider data underlying the data-driven method could be re-examined and remeasured to see whether it truly gave the low value everyone had trusted, or whether something in it had been overlooked. It was the second of these, a fresh look at the collider data, that delivered the next shock. A new and very careful measurement of the most important piece of that data, the simplest Tupian process, was about to come in. And rather than settling the matter, it would deepen the confusion by disagreeing not with the lattice, but with all the earlier collider data it was meant to confirm. The most important single ingredient in the data-driven method is also the simplest, the process in which the flash of light from an electron-positron collision turns into just two pions. This two-pion channel accounts for the largest share of the hadronic vacuum polarization, so its measured value drives the whole data-driven prediction. If you want to check that prediction, this is the number to check, and that is exactly what a group in Russia set out to do. At the Budka Institute of Nuclear Physics in Novosibirsk in Siberia sits a collider with a detector called CMD3, built to measure precisely these low-energy collisions. Over years of careful running, the CMD3 team gathered a large sample of the Tupian process and, in 2023, published their result. It was the most precise single measurement of that channel ever made, and it was meant to strengthen the foundation everyone had been standing on. Instead, it cracked it. The CMD3 value for the Tupian process came out higher than the earlier measurements, and not by a little. It disagreed with a long line of previous results, from experiments such as those using the KLOE detector in Italy and the Babar detector in California, and from earlier runs at Novosibirsk itself. For decades, these measurements had agreed well enough to be trusted and combined into one number. Now, the newest and most precise of them stood apart from the rest, claiming the Tupian process happened more often than the older data said. The direction of the CMD3 disagreement is the telling part. A higher Tupian value pushes the data-driven prediction of the strong force contribution upward, and upward is exactly the direction of the lattice value. In other words, the new CMD3 measurement, taken on its own, pulled the data-driven method up toward the lattice result, and therefore up toward agreement with the Muon measurement. If CMD3 was right and the older data wrong, then the data-driven and lattice methods might not truly disagree after all, and the famous gap with experiment would close from this side too. But that is a large if, and it cuts both ways. Either CMD3 is correct, and a great deal of older trusted collider data is somehow wrong, or the older data is correct and CMD3 is somehow wrong. There is no comfortable middle. Decades of measurements from multiple laboratories cannot quietly coexist with a newer measurement that disagrees with all of them. Someone is mistaken, and the source of the discrepancy has not been found. Physicists have combed through the possibilities, the subtle corrections, the many ways such measurements can go astray, and so far no one has identified what is responsible. The CMD3 tension simply sits there, unexplained. This wrinkle is the part of the Muon story that most popular accounts leave out, because many of them were told before it appeared, or focus only on the headline of new physics. Yet, it is central. The data-driven method was the foundation of the original gap, and that foundation now has a deep, unexplained crack running through it. As long as the 2pn measurements disagree among themselves by amounts large enough to matter, the data-driven prediction cannot be trusted to the precision the comparison demands. The very data that once kept the new physics dream alive had become too tangled to settle anything. So by 2024, the picture had grown genuinely confusing. The Lattice method gave a high value, agreeing with the Muon measurement. The data-driven method, using the older collider data, gave a low value, disagreeing with it. And the newest collider data, from CMD3, disagreed with the older collider data, leaning toward the Lattice. 3 threads, pulling in ways that would not resolve into a single clear answer. Into this tangle, the world's theorists had to deliver a new official prediction, and the choice they made would reshape the entire story. In May of 2025, the Muon G2 Theory Initiative published its second consensus document, an update to the prediction it had issued 5 years earlier. The same large group of experts having weighed the Lattice results, the older collider data, and the unsettling CMD3 measurement, had to settle on a single official value for the Muon's magnet. Their decision marked a turning point in the whole saga. They changed their method. In the 2020 prediction, the strong force contribution had been supplied by the data-driven approach, using the collider data, and that was the value the Muon measurement famously disagreed with. In the 2025 update, the initiative judged that the data-driven approach could no longer give a reliable answer, precisely because of the unresolved tension between CMD3 and the older measurements. With the collider data at war with itself, there was no trustworthy way to extract a single number from it. So the initiative turned to the Lattice method, which by now rested on several independent calculations that agreed with one another, and adopted it for the crucial strong force piece. The consequence was immediate and dramatic. Because the Lattice value is higher than the old data-driven value, adopting it pushed the entire predicted magnet upward. The new prediction landed close to the measured value. The gap that had stood for years, the 4.2 standard deviations that made headlines, the hint of new particles flickering in the muon's cloak, largely dissolved. By the new consensus, there was no significant disagreement between the measured magnet and the standard model prediction, at the precision then available. The anomaly, as a clean sign of new physics, had faded away. It is worth being honest and calm about what happened here, because it is easy to tell it as either triumph or defeat, and it is neither. The Muon did not betray anyone. It behaved, as best we can now tell, exactly as the known particles say it should. What changed was not the Muon, but our best estimate of what the known particles predict. For years, the prediction had leaned on collider data that turned out to be less settled than believed, and once a more trustworthy strong force value was used, the supposed gap closed. The exciting story of the Muon pointing to new physics had rested in part on a number that was not as solid as it looked. This was a sobering lesson in how discovery actually works. The thrilling 4.2 sigma gap had been real, in the sense that the measurement was sound, and the disagreement with the 2020 prediction was genuine. But sigma, as we noted, counts only the noise in the measurement, not the reliability of the prediction. The gap had come not from a new particle, but from a prediction built on shaky ground. When the ground was firmed up, the gap went away. It is exactly the outcome the cautious physicists had warned was possible, and it is why they had refused to celebrate. Yet the new consensus did not bring peace, and this is the crucial point. Adopting the lattice value resolved the Muon against theory gap, but it did nothing to resolve the deeper disagreement underneath. The lattice method and the data-driven method still disagreed with each other. The CMD3 data still clashed with the older collider data. The initiative had chosen the lattice value because it was currently the more trustworthy of two methods that could not be reconciled, not because the conflict between them had been understood or settled. The headline anomaly was gone, but a quieter, more technical one remained, buried a level down in the disagreement between our own tools. While the theorists were reaching this new consensus, the experiment was preparing its final word. The Fermilab measurement, refined to its ultimate precision, was about to be announced, and it would set the standard against which all of this would be judged. On the 3rd of June 2025, the Fermilab Muon G2 collaboration announced its final measurement of the muon's magnet, the culmination of work that began at CERN, passed through Brookhaven, and ended on the prairie outside Chicago. It was the most precise measurement of the quantity ever made, and it will likely remain so for many years. The final value drew on the experiment's complete data set, including the last and best runs taken through 2023, when improvements to the beam and the apparatus had pushed the systematic uncertainties to their lowest level. In one run, the team had added a refined electrostatic system that reduced one of the dominant sources of error by a large factor. The result of all this care was a measurement of the anomaly with a precision of 127 parts per billion, surpassing even the original goal the experiment had set for itself when it was first proposed. It represented more than a fourfold improvement over the final Brookhaven measurement. Crucially, the final number agreed with the experiment's own earlier results, the ones announced in 2021 and 2023. There were no surprises, no drift, no sign that the earlier values had been off. The measured magnet held steady as the precision tightened, which is exactly what you want from a measurement you intend to trust. The world average for the muon's measured anomaly now rests on this Fermilab result, combined with the older Brookhaven one, a value known to better than 2 parts in 10 million, an extraordinary achievement of experimental physics. Think for a moment about the full arc of it. A particle that nobody ordered, found by accident in a cloud chamber in 1936, mistaken for years for something it was not, had its faint internal magnet measured to 11 significant figures by a 50-foot ring that was floated 3,000 miles by barge and shimmed to near-perfect uniformity by hand. Hundreds of physicists, working under self-imposed blindness so they could not fool themselves, opened their sealed envelopes and read off a number that matched their earlier work and set a record for precision. Whatever the theory side does next, the measurement is now essentially settled. The experiment did its job and did it beautifully. That very flawlessness changes the shape of the problem. As long as the measurement was still improving, one could imagine the resolution coming from the experimental side, from some shift in the measured value as precision grew. That hope is now gone in the best possible way. The measured magnet is pinned down far more tightly than the prediction is. The entire remaining uncertainty in the comparison lives on the theory side, in the strong force contribution that two methods still cannot agree on. The experiment has thrown down a challenge that theory has not yet met. The ball, as the physicists put it, is now entirely in the theorist's court. The achievement was recognized widely. The Muon G2 effort, spanning 3 generations of experiments at 3 laboratories, was awarded a major prize in fundamental physics, honouring not a discovery of new particles, which did not come, but the sheer precision of the measurement itself and the decades of ingenuity behind it. There is something fitting in that. The experiment was celebrated not for what it found in nature, but for how exquisitely it asked the question. So the final measurement leaves us in a peculiar place. The number is known, the experiment is finished, and yet the deeper puzzle is not solved, because it was never really the measurement that was in doubt. It was our ability to predict, from our own theory, what that measurement should be. To understand what the quiet panic truly is now, we have to set the simple new physics story aside and look honestly at the disagreement that remains. So what is the quiet panic now, after the headline anomaly has faded and the measurement has been perfected? It is not the thrilling story the early news told of a Muon court feeling the tug of undiscovered particles. That story has for the moment dissolved. The unease that remains is quieter, and in its own way harder to dismiss, because it sits not in nature but in our own tools. Here is the plain shape of it. We have a theory, the standard model, that is meant to predict the muon's magnet exactly. One stubborn piece of that prediction, the strong force contribution, can be computed two independent ways. One way simulates the strong force directly on supercomputers. The other reads it from decades of collider data. These two ways give answers that disagree with each other by about 5 standard deviations, the very level we reserve for claiming a discovery. And the collider data feeding the second method is itself internally inconsistent, with the careful CMD3 measurement clashing with everything that came before it, for reasons no one has found. That is the real disquiet. It is not that the muon misbehaves. As far as our best current prediction can tell, the muon behaves exactly as expected. It is that we cannot yet compute one number in our own theory 2 different ways and get the same answer, and we do not know why. Somewhere in the Lattice simulations, or in the older collider data, or in the CMD3 measurement, there is an error or a misunderstanding large enough to matter, hiding in one of the most carefully studied corners of physics. The muon, in the end, did not expose a flaw in nature. It exposed a flaw in our ability to calculate, and that is its own kind of unsettling. It also leaves the door to new physics not closed, but ajar. The reason the gap vanished is that the initiative chose the lattice value, judging it the more trustworthy. If that judgment is wrong, if the older collider data was right all along and the lattice is subtly off, then the gap reopens and the muon may yet be pointing somewhere. The honest position is not that new physics has been ruled out, but that the muon cannot currently settle the question because the prediction it must be compared against is not yet under control. The muon's verdict is suspended, waiting on a calculation we have not finished. The path forward is clear, even if the destination is not. More lattice groups working independently and under blinding so they cannot drift toward one another's answers are computing the strong force contribution to see whether they confirm the high value. The collider data is being remeasured and re-examined to hunt down the source of the CMD3 tension. New facilities are coming. A different experiment in Japan, at the J-Park laboratory, plans to measure the muon's magnet with a completely different technique, using slow muons in a compact ring rather than fast ones in a giant one, providing an independent cross-check that shares none of the old method's particular weaknesses. The same effort aims to look for a separate, even subtler property of the muon, a tiny lopsidedness in its charge called an electric dipole moment, which would be a clean sign of new physics if it exists. So the Muon story is not over. It has changed from a hunt for a new particle into a reckoning with the limits of precision itself, a test not of nature, but of how well we can pin nature down. That is a less cinematic mystery, but a real one, and resolving it will sharpen everything we can say about whether the known particles are truly all there is. The quiet panic is the sound of careful people, realizing that their most precise comparison rests on a calculation they have not yet mastered and getting to work. Which brings us back at last to the particle still passing through you as you read. A muon is passing through you right now, as one was when we began. It was born a few miles up, when a fragment of some distant cosmic violence struck the air, and it is falling through your body at nearly the speed of light, kept alive on the journey only because its own clock runs slow. You will never feel it. In a fraction of a heartbeat it will be gone, decayed into lighter things, having left no mark on you at all. And yet that fleeting, useless particle has carried us through nearly the whole of modern physics. So let us answer the question the title posed, plainly and calmly. Are scientists quietly panicking about the muon? For a while, yes, in the careful way that physicists panic, which is to lean forward and argue and recheck. They thought the muon's tiny magnet might be revealing a crack in the known laws, a first sign of particles no one had ever seen. As the work matured, that reading faded. The Muon, as best we can now tell, behaves exactly as the standard model says it should. The real unease turned out to lie not in the Muon but in us, in the discovery that we cannot yet calculate one piece of our own theory 2 different ways and have them agree. The Muon kept it secret by exposing one of ours. Step back and see what this single particle has touched. To understand its magnet, we needed cosmic rays and cloud chambers and the accident of its discovery. We needed Dirac's equation and the clean number 2 and the antimatter that came with it. We needed Schwinger's first correction and the restless quantum vacuum, full of flickering virtual particles. We needed special relativity to explain how the Muon reaches the ground and how it survives long enough to be measured. We needed the weak force's strange-handedness, which lets the Muon report its own spin as it dies. We needed the strong force and quarks and gluons and supercomputers simulating cubes of the universe. The Muon is a single thread, and pulling on it unravels nearly everything we know about the small. That is the deeper reason a particle nobody ordered became one of the most valuable in physics, because its magnet can be both measured and calculated to outrageous precision, and because its weight makes it sensitive to the rare and the heavy. The Muon is one of the sharpest tools we have for asking whether our picture of reality is complete. It does not shout its answer. It whispers in the 11th digit of a number, and to hear the whisper we have built rings and supercomputers and decades of patient work. The answer, for now, is that the picture holds, but that our hands are not yet steady enough to read it perfectly. There is a kind of wonder in that, and it is worth holding on to. We live inside a universe that is, at its smallest scales, never truly empty, a vacuum that fizzes with brief flickers of everything that can exist. Every Muon falling through you carries the imprint of that fizz in the strength of its tiny magnet. We have learned to read most of that imprint, and we are honestly stuck on one part of it, and being stuck is how physics finds its next step. The Muon has not finished with us, and we have not finished with it, so the next time you sit still and the world feels solid, remember the soft, invisible rain coming down through your roof, and your shoulders, and your hands, each drop a piece of the sky, each one a sizeless point of charge with a magnet so fine it has occupied some of the best minds alive. Nobody ordered the Muon. It came anyway, and it has been quietly teaching us the shape and the limits of our knowledge ever since.